Okay, going to get started. Last class we talked about electrical attraction, repulsion. We quantified through Coulomb's law electrical attraction, repulsion. This class we're going to talk more about electrical attraction, repulsion, but we're going to explain electrical attraction and repulsion through the electrical field. So that's the basic plan for today. It really builds on last Thursday's class. These are the topics that I want to walk through or talk through. I want to introduce the idea of the electrical field. I want to define the electrical field. So that's going to be maybe 4 or 5 slides on that. I want to talk about computing electrical fields, and we'll look at some illustrations, examples of that. I want to talk about sketching or picturing or visualizing the electrical field, and we will look at some examples, illustrations of that. Then finally at the end, if I get time at the end, I'll just mention or make a few remarks about electrical fields and conductors and insulators. So electrical field in the context of conductors and insulators. So that's the plan. Okay, so firstly, 5 slides or so to introduce the idea of the electrical field and to carefully define the electrical field. So last class we talked about the electrical force, and we discussed Coulomb's law for the electrical force, which characterizes the electrical force between a pair of point charges. But Coulomb's law for the electrical force really has a kind of shaky, uncomfortable foundation to it. That force in Coulomb's law is just some sort of mysterious, we call it action at a distance. So 2 charges separated by some distance mysteriously, strangely interact with one another, exert forces on one another. There's no explanation in Coulomb's law of why the 2 charges separated by some distance interact, attract or repel one another. It's actually the same as an uncomfortable, awkward problem with Newton's law of gravity. Newton's law of gravity, 2 masses separated by some distance act at a distance, interact at a distance. They exert forces on one another over that distance. There's no explanation for how gravity works in Newton's law of gravity. So this is an uncomfortable foundation for electrical force and Coulomb's law, uncomfortable foundation for gravitational force and Newton's law. We could compare it with what, at the time, if we went back 100 years or 200 years, seemed much more explainable forces. Much more explainable forces are contact forces. Like friction is a very explainable force. Tension is a very explainable force because in those cases, right, objects are physically in contact. So it's easier to imagine, easier to picture how the forces, how there's forces between 2 objects when they're in contact. It's much harder to picture how there's forces between 2 objects, 2 charges or 2 masses when they're not in contact, when they're separated by some distance. So that's the background. So the solution to the problem, and this solution is due to a scientist, his name is Michael Faraday. You met Michael Faraday in chemistry because he made a lot of contribution in chemistry, but he also made a lot of contributions in physics. His most famous contribution in physics is the idea of a field. So his solution to the problem of action at a distance between two masses or between two charges, the forces at a distance between two masses and two charges, is that those forces are carried or mediated or conveyed by something we call a field. So the electric force between two charges is mediated, carried or conveyed by a messenger we call the electrical field. The gravitational force between two masses is mediated, carried or conveyed by another messenger that we call the gravitational field. And it's these fields, gravity fields, electric fields, that convey the electric and gravitational forces, and that's what we're going to explore in today's class. There's a little bit of irony here in that with these fields explaining electrical forces and gravitational forces between separated charges and separated masses, in that it's actually these fields that convey contact forces like tension and like friction that I previously mentioned. So the tension force and the contact force is actually at the microscopic level, at the level of atoms and molecules, is actually an electric force. And that electrical force that's responsible for tension and responsible for friction is conveyed by an electrical field. So those contact forces that they thought they understood are actually electrical forces that they didn't understood, and they're conveyed like all electrical forces or all gravitational forces by electrical fields or gravitational fields. So that was a big breakthrough, and we got to thank Michael Faraday for that. Okay, so here's a more quantitative picture of how this works. So I just want to go through this slide because I think this slide's sort of important in understanding in detail how these fields work. So I've got two pictures, one upstairs here and one downstairs. These are pictures of the interaction, the attraction and repulsion that occurs between two charges. And those two charges, I've labeled them Q1 and Q2. So we're going to be thinking about two charges, Q1, Q2. We know those two charges would either attract or repel, depending on whether they're like or unlike charges. So there'll be forces of attraction and repulsion between them. And we're going to picture that situation. We're going to picture it from two different perspectives, right? Firstly, we're going to picture it from the perspective of Q1, that's the charge on the left, exerting a force on Q2, that's the charge on the right. So that's one perspective. That's Q2, the right-hand charge, feeling a force, experiencing a force from the left-hand charge. That's the top figure. The bottom figure is the reverse perspective. That's picturing it from the perspective of Q2, the charge on the right-hand side, exerting a force on charge 1, the charge on the left-hand side. So that's where charge 1 is feeling the force due to the right-hand charge Q2, and that's the lower picture. So that's what these two pictures are. So Q1, Q2, Q1 exerts a force on Q2. Q2 and Q1, Q2 exerts a force on Q1. Look how I labeled the forces in the two cases. This force here upstairs has a subscript 1, 2. By 1, 2 I mean charge number 1 exerting a force on charge number 2. This force down here has a subscript 2, 1. By 2, 1 I mean charge number 2 exerting a force on charge number 1. So that was my notation here. And I've drawn in red and green the force arrows on the two charges. I drew this one as red because the red charge was creating that force. I drew this one as blue because the blue charge, Q2, was creating this force. To this picture, I added the new thing, which is the electrical field. So look at that little cloud. Look at that little cloud around Q1 in the top plot, and that little cloud around Q2 in the bottom plot. That's my cartoon of the electrical field. So the electrical field of Q1 is like a little cloud or shroud that surrounds that charge. And it's the carrier, the mediator of the electrical force that Q1 exerts. And when I picture Q2 and its electrical field, it's electrical field is also like a little cloud now surrounding Q2 that conveys or carries the forces that Q2 exerts on other charges. So the cloud is meant to be a cartoon of the electrical field, and I labeled this one E1 because that's the field of Q1. I labeled this one E2 because that's the field of Q2. And it's because charge Q2 sits in the field of E1 that it experienced the force. It's that field that creates the force on Q2. So here's the little force, the hand, that's being exerted because Q2 is in the field E1. And likewise down here, it's that field that conveys the force on Q1. So that force on Q1 is due to Q1 sitting in the field of Q2, this field E2. And so that's a picture of forgotten his name, Michael Faraday's idea that the fields are mediated, carried, conveyed, the forces are mediated, carried and conveyed by fields. Here we just turned it into an equation to carefully define these two fields. So, you know, we can measure the charges, how many coulombs of charge there are. We can measure the forces, how many newtons of force there are in these two pictures. The field at the location of Q1 is defined so that's the field E1 at this location here, is defined as the force, something we can measure that Q2 experiences, divided by its charge, something that we can also measure for Q2. And likewise down here, the field at the location of Q1, E2, is defined by the force that Q1 is experiencing divided by the amount of charge that Q1 owns. So again, we're defining the field in terms of measurable things. And so these two equations that come along with the two pictures really define this new quantity that we're meeting, electrical field, in terms of old quantities that we've met, force from the last class and charge from the class before that. It's just the ratio of the force on a charge divided by its charge defines the field at the location of that charge. That's the whole idea here. Here I've rewritten that equation. We call it the field equation. It simply says, if you turn it around, that imagine you're a charge, or I'm a charge. If I'm a charge, you're a charge, you've got charge Q, or I got charge Q. If I'm in a field that's strength is E, then I'll experience a force that's the product of my charge and the field that I'm immersed in. And so that's the field equation. A couple of things to note about that is that, like force is a vector, it has strength and direction. The field is a vector, it also has strength and direction. So that's an important thing. Whereas charge is just a scalar quantity. It only has a size and a sign. It doesn't have an orientation or a direction to it like the field and the force do. Okay. Everybody okay with that? Good. We can use this idea to actually then take Coulomb's law for the force between two charges and write down the field that's created by a single charge. So now we got a picture that whenever you've got a charge, Q1 and Q2, for example, surrounding those charges, Q1 and Q2, is a cloud, a shroud of electrical field. And now we can write down, using our field equation, an expression for the electrical field of a charge. So on this slide I've got the electrical field of a positive charge. On the next slide I've got the electrical field of a negative charge. And I'm getting these equations for the fields rather than forces just by using the field equation that we just met on the last slide and Coulomb's law from the last class. Okay, so here's a charge Q, positive charge, and we want to know the field that's surrounding it. And one way we can find the field surrounding it is use another charge, sometimes we call it the test charge, kind of to probe the field, to explore the field by placing it nearby. Because it will experience a force which if we divide that force by the charge of this test charge, Q naught I called it, that will tell us the field. So this is a way of finding out the field of a point charge using another test charge and the field equation here. A couple of things about it. So firstly, the direction. What's the direction of a field? The direction of the field for a positive charge is always directed radially outwards, pointed radially away from the positive charge. So here you see the field, I pictured it as this orange arrow here, is pointing radially away from the positive charge. And wherever you are around this positive charge, the field is pointing radially away from a positive charge. So that's one fact about the field of a positive charge. Second important fact about the field of a positive charge, what is the size of the field of a positive charge? Well, that we get with the field equation. This field here, the size of it, is the size of the force that it's experiencing divided by its charge. Well, the size of the force it's experiencing is given by Coulomb's law. This is just Coulomb's law from the last class. K times the product of the charges divided by the square of the distance. If I divide Coulomb's law by this charge, Q naught, the test charge that we're using to probe the field, explore the field, measure the field, the Q naught in the numerator and the Q naught in the denominator, they cancel out perfectly, and they tell us that the strength of the electrical field of this point charge is just K, Coulomb constant in nature, times Q, the charge of the charge that we're interested in finding the field of, divided by the square of the distance you are from that charge. So that's a simple equation for the field of in this case, a positive point charge. It's just in proportion to the charge, so the larger the charge, the bigger the field, and it's inverse proportion to the square of the distance. The further from the charge, the weaker the field. If you double the distance from the charge, 4 times weaker field, and that's all encoded in here. So this one slide here is an entire summary of the direction and the size of a positive point charge's electrical field. The next slide is just the same thing for a negative charge. I just replaced in the figure the positive charge downstairs here on the bottom left with a negative charge, so the minus sign here. I'm still going to explore the electrical field with a test charge. I've got it sitting upstairs here. And I still want to remark about what is the two key things about this field of a negative charge. What is the direction and what is the size? Well, the direction reverses. In the case of the positive charge, the field lines always pointed radially away from the positive charge. In the case of the negative charge, the field lines always point radially towards the negative charge. So the field direction has reversed from positive to negative charges. That fact explains why, like charges like charges repel and unlike charges attract one another. So that's built into this changing of the direction of the field between positive and negative charges. Field lines pointing away or field lines pointing towards the charge. The size of the electrical field, well, the size is exactly the same formula as the size of the positive charge. You just take the force on this test charge, divide it by its charge, the Q naughts cancel out, you get the same little expression over here. The Coulomb constant times the square of the charge owned by this now negative charge, divided by the square of the distance you are from the charge. So more negative charge is a stronger electrical field. Further from the negative charge is a weaker electrical field. You double the distance from the negative charge, you're going to divide by 4 the strength of the electrical field. Okay, so that's my entire introduction to electrical field. Yes?
Since a negative electric field is pulling towards its point of origin, why do they repel each other?
Okay, so that's a very good question. So let's explain that. I would say, one thing I would say is I wouldn't use the word pulling, because pulling to me sounds like a force, right? I would say I think the electrical field is pointing towards the negative charge and pointing away from the positive charge. So that's one little detail, because I think we typically would use the word pulling or pushing with a force rather than a field. But anyway, your question was, how does this explain attraction and repulsion, I think? Or did I forget it already? Why? Yeah. So let's imagine this is over here. This is a positive charge. So F equals QE. So if the field is pointing this direction, and we've got a positive charge, so I'm multiplying the field vector by a positive number, the charge, I'm going to get another vector, the force vector, that's pointing in this direction. So a positive charge is going to be attracted because it's going to be pushed in the direction of the electrical field vector. If it were a negative charge, now let's think about negative charge, then we're going to again use the field equation. The force on the negative charge is going to be QE again, but now Q is negative. It's got a minus sign in front of it. What does that do to the vector QE? What it does is flip the direction of the vector. It reverses the direction of the vector. So if this is a negative charge, the electrical field is pointing towards the other negative charge, but the force, because it equals QE, is going to be pointing away from the negative charge. And that's repulsion. And so that was a really good question. And that question is really this key thing, that through the fields pointing towards a positive charge and away from pointing towards the negative charge and away from a positive charge, built into that is that like charges will repel one another and unlike charges will attract one another. So no matter what combination you think of, two positive charges, two negative charges, a positive and negative charge, you'll get the attraction and repulsion that we know occurs based on these directions for the electrical field and the field equation. Okay, that's good. Any other questions on this? That's really helpful to ask me questions, because I could go on talking for a very long time, and maybe nobody's with me. So pulling me back is a good idea. Let's look at the relation between fields and charges with a couple of examples. Let's try and do that. Okay, so here's a little problem. This involves the field equation. This is why I picked this problem. We're told that we've got an oil drop that's floating in air. It's just floating there. How could, or like a little raindrop, just floating in there. How could that be? Well, that oil drop is being pulled downwards by the gravitational force, but the reason it's floating, not falling, is it's actually being pushed upwards by an electrical force. So we've got this oil drop, tiny, tiny oil drop, that's floating stationary in air because there's a balance between a downwards pull of gravity and an upwards push of an electrical force. So that's the basic situation. And you can see it pictured in this slide here. Here's the oil drop. Here's the gravitational force, and here's the electrical force. Now, we're told a couple of things about the properties of the oil drop. So we're told the mass of the oil drop is 3.8 grams. We're told the charge of the oil drop, it's minus 18 microcoulombs, so it's negative and 18 microcoulombs. And from that information, charge and the mass, we got to figure out the electrical field that's been placed in. So we're gonna figure this out. I think I'm gonna do this on the document camera. So here we are, and I started the problem already a little bit. I wrote down the the charge, 18 microcoulombs. Of course, I'm going to, when I do a calculation, I better put it in coulombs, so I will do that conversion. I got the mass here. It was 3.8 grams. It's 0.0038 kilograms. I already drew the two forces that we were explaining. There's an electric force up, gravitational force down. They must be equal and opposite if this thing's floating. The key point is that Fg plus Fe, remember they're vectors, and one's up and one's down, so they're in opposite direction. They must be what we would say is equal and opposite. Okay, so that's the first that's the basic idea of this problem. Now, how are we going to find the electrical field in this situation? The way we're going to find the electrical field is first find the electrical force, and then we're going to use the field equation. So this is practice with the field equation. We need to know, though, to start it all going, the gravitational force. But the gravitational force we can figure out by just that equation, the size of it here I'm figuring out, mg. That's the gravitational force on an object in the Earth's gravitational field. It's the gravitational force on you. If you take your mass, it's the gravitational force on the oil drop if we take the oil drop's mass. So this is a famous 211 equation that you'll never forget, is my hope. Okay, so we've got to multiply the mass by the acceleration of gravity. Acceleration of gravity is 9.8 meters per second squared. It's also a number we never forget. And if we do that calculation, I won't write down the two numbers. I got 0.037 newtons. Remember the mass was 0.0038. And remember the acceleration of gravity is almost 10 meters, almost 10, right? 10 meters per second squared. So the force as a number is about 10 times bigger. If that's the gravitational force, it must be that this upwards electrical force, whose size, the field equation, is equal to this 0.037 newtons also. So this is also 0.3037 newtons, just based on the balance. Well, look, now you can see the route to solving this problem. We found the gravitational force, we found the electrical force, we know the charge of the charge that's floating there, of the oil drop that's floating there. So if we know the force on the charge and we know the charge of the charge, we could use the field equation to figure out what the field at the location of the charge is. So let's do that. The first thing I'm going to do is find out the size of the field. And then we'll talk about the direction. So just to make that really clear, I'm going to find the size of the electrical field. That's what the little stick men standing up either side of the E are. The size of the electrical field based on field equation is going to be the size of the electrical force, which we figured out, divided by the charge. The charge is this 18 microcoulombs, and it's divided by the size of the charge. So everything's just sizes here. I'm only worrying about sizes. Let's do directions next. So I just got to plug in the numbers. I've got to plug in 0.037 newtons divided by 18 microcoulombs, and if you do that, I won't write them out because they'd be unreadable, and I can't find my solution. I got 2,069 newtons per coulomb. So that's 0.037 divided by 18 microcoulombs. So 18 times 10 to the minus 6 coulombs. And I got that to be about 2,000 is the number. And the units? Let's talk about the units. What are the units? Well, the units are force divided by charge is newtons divided by coulomb. So field has the units of newtons divided by coulomb. Okay, everybody okay with the size? Now let's do the direction. The direction. The force, so this comes to the question that was asked on the field equations and the electrical field. the electrical force is upwards. If we had a positive charge, that would mean that the electrical field would be upwards. Because if you've got a positive charge, the field and the force are in the same direction by the field equation. F equals QE because E is positive. Q is positive. If you've got a negative charge and the force is upwards, for a negative charge, that means the field is downwards. Because the field and the force are in the opposite directions if you have a negative charge. Because the minus of the negative charge flips or changes the direction of the field and the force with respect to one another. They're in opposite directions. So no calculations or formulas here, just that reasoning. Because we got a negative charge and the force is up, that means that the field is down. So I'll just write FE up in some unreadable writing, E down. And so that's the direction. Everybody okay with that? And that's a field equation. Very famous equation, very important equation, beautifully simple in a way, beautifully simple explanation of how forces work. One charge produces a field, the other one sits in it, experiences it in an amount that depends on the strength of the field and the size of its own charge, and that's how you get the force. It explains everything. Thank you. Thank you, Faraday. Okay, I will mention that this is not, this little problem sounds a curious and made-up problem, but actually somebody got the Nobel Prize for doing this experiment, floating oil drops in air with electrical fields. Robert Millikan, US scientist, got the Nobel Prize for floating oil drops in air because he did that. He performed that experiment with tiny oil drops and was able to measure the electronic charge of a single electron sitting on an oil drop. And so it's a very famous, it's a problem, but it's a very famous experiment that was the discovery of that basic unit of charge, 1.6 times 10 to the minus 19 coulombs. Okay, here's a quiz question. Let's go to the quiz. I'm going to publish this if I can. What time is it? It's 10:02. Where is it? Oh, look at that. What a good guess on my part. But not quite a good guess because that I don't want it to be due at 10:02. So let's make this 10:05. And let's publish this if I can. So this question says you got two charges in the, oh, you can't see anything, can you? Sorry. If you ever think that I think, so it's mind reading, if you think that I think that there's slides on the screen, but really there's something else on the screen, just let me know, because I can go on for a long time thinking there's something, slides on the screen, I'll be changing them, I'll be talking about them, and they're not even there. So I would definitely remind me of that. That happens. We got two charges. We got a blue one on the right that's big, and a smaller one in size of charge as well as dimension, that's on the left in red. And the question asked you to compare the forces that Q1 and Q2 experience, the size of the forces, and the fields that Q1 and Q2 create. Compare the size of the fields, compare the size of the forces. Are they the same size? Are they different sizes? That's the whole question is about that. And there's just four combinations, right? The fields and the forces are the same size, or the fields and the forces are both different, or combinations of different and same. So yeah, think about it. Okay, let's solve this problem. The answer is, when we compare the forces on the two charges and we compare the fields at the location of the two charges, the two forces have the same size, exactly the same size. The two fields, on the other hand, have different sizes. The big charge Q2 creates a bigger field. The small charge Q1 creates a weaker field. This is a very important fact that really goes to the heart of the difference between forces and fields. It discriminates forces and fields. So the forces between two charges, like the forces between two masses, like the force between you and the Earth, for example, they're always equal and opposite. So forces always come in equal and opposite pairs. So if you've got Q1 and Q2, those two forces are going to be equal and opposite on those two charges. Just like the force of me on the Earth and the Earth on me sounds ridiculous, but they're the same. Same size, opposite direction. I exert a bigger force on the Earth as the Earth is exerting on me. So the forces are the same size, but the fields are different. So the big charge creates a bigger field. The little charge creates a smaller field. So the fields depend on the size of the charge. They grow with the amount of charge. Now, the big charge creates a big field, but Q1, the little charge, because it's a little charge, only feels it a little bit. And those two facts cancel each other out, and you get the same size force. The little charge only creates a little field, but the big charge sitting in it feels that field a lot. And those two facts, again, cancel out, so you get the same size force. So this is a very important discrimination between fields and forces, and what's equal and what's unequal. Everybody okay with that? Yes?
If you were thinking about this like mathematically, Coulomb's law would show that the forces are equal because you would use both Q1 and Q2 in Coulomb's law?
Yeah, that's a really good way of thinking about it. If you like to think mathematically, or you like to think of equations are great because we might not inherently want to deal with equations, but actually they're really nice summaries of how things work. That's the way I think about equations. And Coulomb's law tells you straight off, right, exactly as you point out, the forces must be the same size because you're just multiplying Q1 and Q2. It's only when then you could think about, well, what does the field equation, if the forces are the same, tell me about the fields? In one case, I'd be dividing by Coulomb's law by big charge, the other case by small charge. Immediately, you see that the fields are different. I think this is a way better answer than mine, actually. Thank you. Okay. Let's go on, talk about superposition. We talked about superposition of forces in the last class. Now I'm going to talk a slide or two about superposition of fields in this class, and then we'll look at an example of superposition of fields to get some practice of it. Okay, so just like electrical forces superimpose, those force vectors add together, beneath that, the reason for that is that electrical fields also superimpose. The electrical field vectors also add together as vectors. And so everything we learned about superposition for electrical forces, we can apply to electrical fields. And that's what I've written down here. And that's what I'm picturing here. So let's just walk through this quickly. Here I'm imagining a case of, I'm coming over to this side of the room because I don't think I'm over here enough. I think I'm way over there too much, but I get attracted to the computer. So I'm going to just come over here for a bit, get a different perspective. Two charges. Remember these two charges from the last class? There was the orange one and the olive one. These, in the last class, created electrical forces on a third charge. In this case, they're just creating their electrical fields surrounding them. So this space around here is the superposition of the electrical field due to charge number 1 and the electrical field due to charge number 2. And so here's the electrical field, pictured it as this orange arrow here due to the orange charge. This must be a positive charge because the field is pointing away from it. And here in olive, right, this is the electrical field vector for the olive charge. It must be actually a negative charge because the field's pointing towards it. So we got these two fields that we pictured as these two vectors. We drew, or I drew, these two fields based on equations for the electrical fields of a point charge and the directions for the electrical field of the point charge. And the total electrical field, the net electrical field, is then just going to be the vector addition, the superposition of E1 and E2. And I drew that vector here. It's this teal colored vector here, and I wrote that idea down here that superposition of fields applies just like superposition of forces. And so I put that on. Don't know which light switch I was hitting. We'll find out. There. Superposition of fields works just like superposition of forces. This slide just shows you how I added together the two field vectors to create the resulting net total electrical field. Just this rule about picturing the addition of fields. You draw the first field vector, that's the orange E1. And then you draw the second field vector, that's the olive E2. You draw it with its tail starting at the tip of the first vector, and then the resulting vector goes from the tail of the first vector to the tip of the second vector. So this is how we picture the addition of the two fields. Okay, so let's look at an example, an illustration of superposition of electrical fields. I'm just going to take two charges, 2 point charges, and we're just going to superimpose the fields of those two charges. So this is the arrangement I picked to figure out the electrical field of two charges. What's the most famous molecule? Well, when I asked ChatGPT the most famous molecule, the top molecule was the water molecule. It is by far and away the most famous molecule. And we're going to look at it here because that molecule is basically, electrically, it's an arrangement of a positive and negative charge. It's got a positive and a negative end to it. And we call that an electric dipole. That's just the name we give it. We're going to figure out the electrical field of that electrical dipole. It's the most famous molecule because of its electrical properties. So its electrical properties just emerge from the fact that there's two types of charge that attract and repel. And out of that emerges a water molecule built out of atoms, hydrogen and oxygen atoms, that has amazing properties. It has, because of its electrical properties, it acts as a outstanding solvent. And its solvent action is the basis for life. So I've said this in every class now. We're bags of salt water, little cells of salt water. There's fluids inside the cell and outside the cell. That's salt water, and that salt is dissolved because of the electrical properties of the water molecule. So without this electrical property of the water molecule, there would be no there would be no salt water, there would be no us. So it gives rise to our lives. Also gives rise to the electrical properties of water molecules give rise to capillary action, which is essential for kind of plant and tree life, right? Drawing up water from through the roots to the plant or to the tree. So it gives life to plants and trees as well. The electrical properties of the water molecule are also responsible for a very interesting feature of water, is it's a superb absorber of heat energy. It's a superb reservoir of heat energy, and because of that it is a big part of maintaining a reasonable temperature, not too hot, not too cold on Earth. So it makes the water on Earth makes the Earth habitable. So that's another good reason. So I just listed 3 big reasons you're alive, plants are alive, and the Earth is habitable for being interested in the electrical properties of a water molecule. So that's why we're going to do it. Okay, so here's now a cartoon version of a water molecule. As I said, it's got a positive end and a negative end. The negative end is the oxygen and the positive end are the hydrogens. But here we're just depicting it as a positive charge and a negative charge. So here are the 2 charges. I dropped them on this imaginary x-axis here. I have this imaginary vertical y-axis here that bisects the 2 charges. And what we're going to figure out is the electrical field at some location here on the vertical axis. So at some point midway between the 2 charges. This point I labeled it P. The electrical field there is the superposition of the electrical field of the positive charge and the electrical field of the negative charge. So I actually sketched that on this plot. So E1, remember if you've got a positive charge, the field points radially outwards, away. So this is the field E1 of the positive charge. And then this E2 down here, this arrow, this is the field of the negative charge. Remember, for a negative charge, the field points radially towards the negative charge. So this is that field here. You notice one interesting thing when I drew these 2. I drew them the different directions, the ones away from, ones towards the respective charge that's creating them. The other thing I did was to draw them the same size. Those 2 fields, Q1 and Q2, are the same size. They're the same size because they're equal distance, R and R, these dashed lines here, from equal sized charges. And so they are the same size electrical fields. So that's all pictured on here. There's a couple of bits of geometry that's pictured on here. A is the distance of the positive charge or the negative charge to the left or to the right of the origin. So right here. So that's the A. Theta is the angle that this dashed line makes to the horizontal, either this theta or this theta. It's also the angle that these vectors, E1 and E2, make to a horizontal line, because the vectors act either towards the charge or away from the charge. And the dashed lines are the lines that are away from or towards the charge. So that's just a little bit of geometry. Okay, so this one I'm not going to do on the document camera. It would take me way too long. Subscripts are really tough for me on the document camera, so we're just going to do it on the slides. This looks bad, I would be willing to say, but I don't think it's so bad as it first looks. If you just take a few breaths and relax, and we'll walk through this. So this is the picture from before. To the picture, I've added a little more annotation, and this slide is about calculations related to that annotation. Specifically, if we're going to add our job is to add E1 and E2. That's all we've got to do. Just got to add E1 and E2. To add these 2 vectors, to add E1 and E2, what we're going to do is break them down into horizontal and vertical components, X and Y components. And then once we got the E1 in X and Y components and E2 in X and Y components, we can add those two vectors together very straightforwardly like numbers. So that's basically the plan. We did this in the last class. So, okay, so that's the basic idea. To get us started, I pictured this vertical red line, this horizontal red line. They're the X and Y components of E1. Right? They're the components, the portions, the parts of E1 that are in the horizontal and vertical directions. Just a picture of them. And same thing down here for E2. This is the X and the Y components of, this is the X and this is the Y components of E2. The horizontal vertical components of E2. And it's the values of these components that we want to get. My starting point for E1 is that using that version of Coulomb's law for the electrical field, this is the field that is creating. The strength of E1, the size of this vector here, the length of this hypotenuse is just KQ over R squared. And the same thing for E2. The length of this line here, this hypotenuse of a right-angled triangle, is just also KQ over R squared. So the two fields have strengths that are just proportional to the charges. They're both Q's. Inverse proportional to the square of the distances. They're both R, distances R away, times the Coulomb constant. K in, so it's KQ over R squared in both cases. To find the X and Y components, all I need to do is multiply the KQ over R squareds by either cosine thetas or sine thetas. See, the cosine theta, which is adjacent to the theta, picks out the horizontal components. The sine thetas pick out the vertical components, because the vertical components are opposite the angle. So to get E1x from E1, I just multiply by cosine theta. Same thing for E2x, just multiply by cosine theta to get the horizontal components. For the vertical components, I just multiply by sine theta. Here's the sine theta for E1's vertical component. Here's the sine theta for E2's vertical component. So just multiplying by sine thetas and cosine thetas. I hope that's fine. That's all I'm doing to find the components, except one important detail. That's getting me the size of the horizontal and vertical components. But I want to get the sign right. And I use the diagram for the sign. Coming over to see you guys again. The vector E1 points partly towards the right, we'll call that the positive direction, and partly up, also called that the positive direction. The vector E2 points partly towards the right, the positive direction, but partly downwards, the negative direction. So if you look here, I put in by hand, as well as multiplying by sines and cosines, I put in a plus, a plus, a plus, and a minus. This E2 vector has a negative, importantly has a negative y component, a negative vertical component. And I just read it off the picture. So now at this stage I've got the two components, x and y components of the two vectors, and all I've got to do is add these up. So let's just do that on the next slide. Where the earth am I going? Which is what I've done here. So now once you've got your vectors in your x and y component language, you can just add up all the x components to get the total x component, add up all the y components to get the total y component. As simple as that, to adding together the vectors. You have to be concerned or worry about the signs of the x and y components, but you're dealing with just numbers that can be positive and negative in your vector addition at this point. EY, that's the vertical component of the resulting vector that I pictured here. It's E1y plus E2y. These were equal and opposite. One had a minus sign, one had a plus sign, but they're the same size, and so there's no y component. And you could see it straight off in the picture. We didn't really need to do the calculation. One field's going down by some amount, the other field's going up by some amount. They're equal and opposite amounts, so they cancel out perfectly in the vertical direction. It's only in the horizontal direction you get a field, so we've got to get Ex is equal to E1x plus E2x. I've got to add these together. And if I add those together, I get this little expression here. 2kq divided by r squared times cosine theta. It's just the sum of two equal terms that were kq over r squared times cosine theta. I apologize, I don't know what these little hats or arrows are on here. It must be left over from something else. So this is our answer upstairs here. This is the answer to the superposition of the two fields, of the two charges. This is the electrical field of the arrangement of two charges that we call an electrical dipole. However, I did rewrite it here because I wanted to show you an important thing. You can replace the cosine theta with just basic trigonometry. It's an angle in a right angle triangle. You can replace the cosine theta with the adjacent of that angle divided by the hypotenuse. The adjacent is that distance A of the charge from the origin. And the opposite is that distance R between the charges and what we call the field point. We're evaluating the field. So I just replaced the cosine theta with A over R. It's just the definition of cosine theta as adjacent over hypotenuse. When you do that, you get this little expression here. And we typically do this because it tells us a couple of really important things. It tells us, firstly, look at this r cubed that is now there. The field of a dipole, electric dipole, doesn't fall off as 1 over r squared like a point charge. This field of a dipole, a positive and negative charge, falls off as 1 over r cubed. And that's actually a key feature of the water molecule. When you've got a field that falls off as 1 over r cubed, you can get a strong field nearby the water molecule, so it might hang on to neighboring water molecules, but that field quickly disappears. So if you, for example, double the distance from the water molecule, so double r, how's the field going to change? It's going to decrease by 2 times 2 times 2. 2 times 2 times 2 is 8. So the field is going to get weaker really quickly. It's a 1 over r cubed field. It's a really amazing result from this. That's one important point. Second important point is that the overall strength of the field is not just determined by the charges, but it's determined by the separation of the charges as well. See in the numerator here? QA. That's charge times 2a is the separation. And actually you can see Q times 2a. That's what we call the dipole moment. We give it a symbol P. It's a measure of the strength of the dipole. The dipole gets stronger not only by increasing the charges of the Q and the minus Q, but also increasing the separation of the charges. And what's unique and special, wonderful about water is that its dipole moment is really big. The product of the amount of charge on the positive and negative ends of dipole and the separation of the positive and negative ends of the water molecule is extremely large, unusually large. It's how water inherits all these properties that are dissolving salts so we can live, capillary actions so plants and trees can live, absorbing heat so the planet can live. And so all of that comes out of water molecule having a large dipole moment, which is a emergent property from there being positive and negative charges that attract and repel depending on whether they're alike or different. Amazing thing that such a simple system can give rise to such amazing results of atoms and molecules and cells and whatever. Okay. Everybody okay with that? There was a bit of math there, but the ideas underneath it are really kind of amazing, I think. Okay, I want to show you how to picture electrical fields. And we visualize electrical fields with field lines. And so I've got a handful of slides introducing and showing you field lines. So we can, for at least a little bit at least, relax from the equations. Okay, this is a picture of the electrical field of a single positive charge. Here's the single positive charge. Now, I better be careful. This is a picture here is two-dimensional. But it's really a two-dimensional representation of a three-dimensional field, a cloud or shroud that surrounds the charge. We picture the field using field lines. And here in orange with these arrows, these are the field lines. So when you draw field lines, they indicate or they reveal both the strength of the field and the direction of the field throughout space. So how do they do that? They reveal the strength of the field throughout space from how closely or loosely the field lines are packed together. So for example, the field lines are packed together tightly near the positive charge. So look, they're really packed closely together here. And that's where the field is strong. The field lines are packed loosely together far from the charge. And that's where the field is weak. So the loosely packed, tightly packed is indicating strong or weak electrical fields. That's how they do that. What about the directions? The field lines always point in the direction of the field. Upstairs here, this arrow here is pointing up because the field is up, away from the positive charge. Downstairs here, this arrow is pointing down because the field is down, away from the positive charge. This arrow on the left is pointing towards the left. This arrow on the right pointing towards the right. These are the directions of the field on the left and right, which is again away from the charge. So the arrows tell the direction of the fields. A couple of rules. The field lines always begin on positive charges. No exception whatsoever. Right? Field lines only always begin on positive charges. So whenever you see a positive charge, you should think of it as a source of field lines emerging from it. Field lines also never cross. You don't want to draw a picture where field lines cross, because if you did draw a picture for where field lines cross, remember that the field determines the force. Well, if the field lines cross, which would mean that the direction of the field is ambiguous, right? It means that the direction of the force is ambiguous, and we're not ambiguous in physics. The force is in a certain direction, the field is in a certain direction. So field lines don't cross, hence forces don't have ambiguous directions. Next slide is just the case for a negative charge. Nothing really additional to say. The negative charge has field lines pointing towards the charge rather than away from the charge, because the field points towards the charge rather than away from the charge. We think of negative charges as, we said that positive charges were the source of field lines. Negative charges are what we call, the technical word is sink of the field lines. It's where the field line, it's like the drain that the field lines go down. So if you want to think about positive and negative charges in terms of sources and sinks of field lines, that's a good way to think of it, and we'll talk about that more in the next class. Again, where the field lines are closely packed, that's strong electrical field, so near the negative charge. Where the field lines are loosely packed, that's weak electrical field, far from the charge. Everybody okay with those two? And if so, we'll look at a couple more pictures. This is the dipole. This is the dipole. This could be a water molecule. This is what the field looks like around a water molecule. It's quite complicated but beautiful near the molecule. But if you go far away from the molecule, actually it vanishes pretty quickly because of that 1 over r squared, 1 over r cubed fall off of the water molecules, the electric dipole's electrical field. So here's the positive charge, here's the negative charge of our electrical dipole. Here around the positive charge, the field is strong. Here around the negative charge, the field is also strong because the field lines are closely packed. We see that immediately. On this bisector, remember in our calculation we worked along the bisector between the positive and negative charge. You see the field is sweeping simply from left to right along the bisector. That's what we found by our calculation. So we actually computed this direction and we computed this strength. And we saw, if you remember back to the calculation, we saw that the field did go left to right in the direction from the positive to the negative charge. Basically, the field lines are sweeping out of the positive charge and around to the negative charge. Here they go, these ones upstairs. Here they go, these ones downstairs. Imagine these field lines that are coming out of the positive charge. If there was just a positive charge, they spread out into entire space, we get a 1 over r squared field. If the positive charge has a nearby negative charge, like the electric dipole, then those field lines that are coming out of the positive charge are actually going to sweep out but be collected by the negative charge. They can't escape the negative charge. They pour out of the positive charge, get drained into the negative charge. And you see this here. It's like water coming out of some faucet here, the positive charge, and then going down the drain over here, the negative charge. So they're being collected. This is the reason the field gets much weaker than 1 over r squared. It gets weaker as 1 over r cubed because the field lines aren't allowed to escape. They get captured by the negative charge. So you see out here, the field lines are getting really widely spaced. The field is getting much, much weaker. It's this 1 over r cubed, not 1 over r squared field. Okay. Oh, I want to show some demos of this. Yeah. I'm getting extremely anxious about time, just so you know. So I'm going to show you some demos. I better explain what I got. I've got this thing in my right hand. What is this? Not a hairdryer. It's a portable Van de Graaff generator. Remember that thing that you could create or harvest electrical charge? Well, that's what I'm going to do here. I'm going to turn this handle. I'm going to harvest electrical charge. That charge flows along these wires, and it's going to flow on the wires to this box that I'm going to put on the document camera. And this box, I can put in this box arrangements of charge. So I can deposit the charge from the Van de Graaff on an arrangement of charge in this box. So let's look at that. Okay. Wrong slides. Now you get a better look at the box. This green fluid here, what is this? This is actually castor oil. So it's cheap oil. You can just buy it at the supermarket. And in it is put it's green-colored flock. Flock is just little flakes of fabric. You can buy that at Michael's. So you can do this at home. So it's just these little fibers in oil. The interesting thing about these fibers is that they line up with electrical fields. They align themselves with electrical fields. And so if I put this arrangement in a region of electrical field, then the little fibers in the castor oil will line up and show me what the electrical field lines look like. So that's what we're going to do. Right now I've got I'm going to charge up this guy here on the left, this guy here on the right. I'm going to make this guy positive and this guy negative. I'm going to make an electrical dipole, like a water molecule. And so I'm going to do that, and we're going to see we're going to actually see the field. I mean, you might have been thinking, he's going on about this invisible field. I don't really actually believe it. Well, I'm going to show you it, if I can. if it really works, which it's not. Let me try again. I've got a plan B here. If it doesn't work. This is really beginning to hurt, actually. I'm being extremely uncomfortable. But I will note it on Strava as my exercise session for the day. Okay, I hope you can see at least a little bit this pattern that is emerging. So I think you can see threads coming out from one of the charges and heading towards the other charge. So this is the electrical field between those two charges. And we can maybe expose it a little bit more before I have a heart attack or something. Yeah, I'm pretty sure I can kind of see the pattern. So this is a dipole. I'll show you one more. Hopefully this will work easier. I was going to show you one more, but I've lost it somehow. Here it is. This is a second arrangement. This is a second arrangement where instead of 2-point charges, I'm going to have this charge plate on the left and this charge plate on the right. And so let's charge this up. And this one seems to work better. So these are field lines that are running from one plate to the other plate. And you see the directions of the field lines. Look here, I can see them individually running across here between the plates. At the end, you see the field lines curl around like we did with the positive and negative charges, the simple point charges. Okay. The first demonstration was this arrangement of electrical field, the dipole. As I say, this is a classic example of this as a water molecule. This second arrangement is an arrangement that's the field of a positive and negative plate. The classic example of that is a cell membrane. In a cell, in the human body, for example, there's a electrical charge on that sort of fatty lipid membrane on the inside and outside of that membrane, and that creates an electrical field through the membrane that it looks exactly like this. So we're seeing the field in a cell here. Look, I've run out of time. In the slides, I do have one more example. You might want to take a look at that. There's also, because I ran out of time this class, I ran out of time every class with the last example. And so there is a video of it. There's actually, if you look online, there's a bunch of video examples that you might want to look at. Some are related to homework problems, but to give you a bit more practice, because I'm limited how many examples I can do in class. So basically, to summarize today was electrical field. It's how the electrical force works. It's the mediator, carrier of electrical field, and we worked on a bunch of examples of the field equation and equations for electrical field of point charges. I'll hang out here if you've got any questions.
describe it.